On this last part of the acids and bases unit, we will talk about titration. You have seen titration in chemistry 20 when you were dealing with a strong acid and a strong base, hydrochloric acid and sodium hydroxide usually is the one that you have been doing. So they are very close to each other, buffer and titration. They are very close to each other, but they are very different between each other because a buffer is a solution that it is resisting the change of the pH, while titration is a reaction that is happening. And then based on this, we build that is known as the pH curve, which we took a look and saw it the day before. So when we are talking about titration, well, today we will see titration and mostly we'll focus on titration calculations. When we see titration, titration is happening between those three situations: strong acid, strong base. Okay, you have seen this in Chem 20, sodium hydroxide and strong base, and hydrochloric acid, strong acid. So something like this. The second situation is when we have a weak acid and a strong base. Weak acid and a strong base. So let's say that we have strong base, something like this. And then the third situation is when we have a weak base and a strong acid. As you notice here, a weak base and a strong acid is, let's say, ammonia. Okay. The thing that you notice on all those three cases is that titration is a reaction that is happening between two entities, one acid and one base, in which at least one is strong, at least. But you have a case that there are two that are strong, like at the strong acid and strong bases. When we are talking about titration, what do we see? Because titration, even when we see the curve, the pH curve at titration, as we see that is known as the equivalent point. So let's suppose that we have a situation like this. So equivalent point, which is the inflection point of the graph, is the point where the same number of moles, if 1:1, which is, this is what you will see on most of the, on 99.99% of the cases, the same number of moles of the acid and the base are being part of, are in the reaction between each other. So this is known as the equivalent point. Okay, since we are dealing with the same number of moles, then the number of moles, if we know the concentration and the volume at the equivalent point, what we have is that the concentration of the base times the volume of the base is equal to the concentration of the acid times the volume of the acid. Okay, whatever we are dealing with. So let's suppose that we have a strong acid and a strong base, because this is what the pH curve is representing. And what you are doing here is you are adding the strong base and you are looking for the pH. Now, when we have the strong acid and the strong base reaction, we can calculate this volume. We can see from the graph what is this volume here. And the pH that you are expecting it to be, it is equal to 7. Why it is like this? Why it is like this? Because let's suppose that with a strong acid and a strong base, because this is the situation here. How do we know, first of all, how do we know that we are dealing with a strong acid and a strong base? Just by looking at the graph. How do we know that we are dealing with a strong acid or strong base? Because the starting graph here is very flat. See here? This is an indication that you are, there is no curve at the beginning. This is an indication that you are dealing with a strong one, okay? Now, this is a reaction that will go to completion. There is no equilibrium here, okay? And as a result of this, the product that are formed are liquid water and sodium chloride. None of those products here affect, no, they do not affect the pH, because the pH is affected by the concentration of hydronium, H3O plus, or proton, because it's the same thing, and the concentration of hydroxide, OH minus. So what are you having on this case? Since everything is used, then we can say that if we have, let's say, 1 mole or 10 moles for that matter, let's say 10 moles of hydrochloric acid reacting with 10 moles of sodium hydroxide, then what we will have here as a production will be 10 moles of water and 10 moles of sodium chloride. But since those 10 moles of water and sodium chloride do not affect the value of pH, if we don't have any H plus or OH minus here, then they are all used up because it is a 1-to-1 ratio of hydrochloric acid and sodium hydroxide, then we can say that the pH at the equilibrium is equal to 7, which is a neutral situation. Now let's see the second titration type. Speaking of this, we said that we will have strong acid, strong base, strong acid, weak base, strong base, weak acid. You will never ever see in the course of chemistry 30 a weak acid and a weak base, even though that even on those cases may happen a titration, but you will never see something like this. So when we have strong acid and a weak base, then what are you expecting based on just saying this, that the strong acid is added to a weak base? What are you expecting that the solution be? Acidic or at the equilibrium? Acidic or basic or a neutral one? I think that will be acidic. Yeah, because you have a strong acid here, so quote unquote, the power goes to the strongest entity. And the strongest entity is acidic, strong acid. So therefore, at the equilibrium, the solution at equivalence point, not equilibrium, equivalence, at equivalence point the solution will be acidic. So this is how you will define that it is an acidic solution that you are dealing at the equilibrium point. Now, if it is an acidic solution at the equilibrium, what are you expecting that the pH will be? What is the value of the pH at the equivalence point? Below 7, less than 7. So it is somewhere between, let's say, 4 to 6.5, something like that. Something like that. An example of an acidic or strong acid and weak base in terms of the pH curve will be something like this. You have the pH measure here, and then what you are doing is you are adding the strong acid into the weak base. And a very good and common strong acid is hydrochloric acid. Now, when we are starting at high point because we are dealing with a base, okay? Since we are adding acid, we are dealing with a base. How are we starting, as a flat or as a curve? And is it curve up or curve down if we are doing, but it is a weak base that we are dealing here. So strong acid is added. And what do we have here to start with is a weak base. Since it is a weak, we'll start as a curve. Now, a base has a pH that is higher than 7, okay? Higher than 7. And we are expecting that will go below. So therefore, will be curved down, will be something like this. And by the way, this part here, it's not counted as a buffer area or region. Okay, then we will see the change of the pH that is small, meaning that you are dealing with a buffering region, and then we'll go down very fast. We'll change the attitude like this, and then we will have a pH here that is less than 7, somewhere between 4 and 6, 6.5, somewhere like this. So this is the equivalent point, which again, it is the same number of moles if the ratio is 1 to 1, and this is what you will see most of the cases. So the concentration of A minus times the volume of A minus is equal to the concentration of the base times the volume of the base. Okay, now let's see what happened when we have a weak base, like we, even as example, this is what we brought. Ammonia, we are adding on it hydrochloric acid, a strong acid, and then as a result of this, we will have NH4Cl in aqua solution. This is a salt that is formed. Okay, now, however, when we see this being in an aqua solution, this will be broken down into NH4 plus and Cl minus in aqua solution because it is solubility. So now, as you see here, you see that the result, or what do you have in the product, is NH4, which is what? Is an acid or is a base? In your, even in your data booklet. So is it able to donate or to accept a proton? Will be donating a proton based on the Brownian-Lowry's theory will donate a proton. So this is an acid. Okay, that means that the pH, this is why the pH is less than 7. So keep in mind when we are talking with, or when we are looking at a strong acid and a weak base, we know that the strong, whatever is it, acid on this case, will take the power and make the solution at the equivalence point as an acidic one, because the same number of moles that will react here will be the same. So the same number of moles of ammonia and the same number of moles of hydrochloric acid. And then as a result of the completion of the reaction, we will have an H4 as a plus in an aqueous solution, and Cl that does not affect the pH value at all. So therefore, what is affecting the pH value and what is left at the equivalence point is just NH4 plus, which is an acid, and therefore the pH will be less than 7. So this is the reason, but the way that you remember it, that will be an acid or acidic solution, is because the strong takes the power. But you cannot say that as an answer, as a scientific answer. So now let's see the third case that we will observe at the titration when we have a weak acid and a strong base. As I said, strong will take the power. Therefore, what you are expecting is that at equivalence point, where the number of moles for the acid is the same as the number of moles for the base, okay, at a 1-to-1 ratio, which is 99.9999% of the cases that you will see on chemistry 30, will be, the pH will be a basic one, basic solution. A basic solution means that the pH, it is at a value greater than 7. An example of this will be if we have HF, that is a weak acid that is reacting with a strong base, let's say the most common one, NaOH. They are 1-to-1 ratio. So if we have 1 mole of HF reacting with 1 mole of NaOH, as a product here, what we will have will be water and NaF in aqueous solution. So then at the product here, we'll have 1 mole of water and 1 mole of NF. However, since this is an aqueous solution and it is very soluble, high solubility, will be Na plus as ion and F minus as aqueous solution. So when at the equilibrium, when we have the same number of moles of weak acid and the strong base, what do you see here is 1 mole of F minus. Now F minus based on the Brownian-Lowry, is it a base or is it an acid? It's accepting or is it donating a proton? So it is accepting, is able to accept a proton. Therefore, will be a base. So the solution is basic solution. So you remember that the strong, either acid or base, takes the power, but the reasoning, the scientific reasoning is that what do you see at the product at the equilibrium is either entity that is able to donate the proton, making it acidic, or is able to accept the proton, making it a basic solution at the equilibrium. So the pH curve on this case, when we are adding a strong base into a weak acid, the pH curve will be something like this. So in this case, when we are adding NaOH, we will start with a low pH because we have a weak acid. So since we have a weak acid, the start point is somewhere in here, let's suppose. Since we have a weak acid, what do you think that we will have as the start? A flat start or a curve start, curve up or curve down? It's a curve up. Great. It's a curve up, and this part here, it is not even considered as a buffer regioning, and then it starts with a slight increase, and then it goes to a rapid increase, changing the inflection, making this as the equivalent point. Okay, making this equivalent point. Okay, so when we have more than one hydrogen to release, just let's deal with this first. This region here is known as the buffer region. We said that, and there is a mistake in your textbook saying that even this region up here is a buffer region, but no, it's just from the starting point to, you can even go up to the equivalent point, but just go just at this region where the pH is slightly increasing. The same logic is in the second graph here. We do not consider the part that it is either curve up or curve down for the weak, but this will be the buffering region. And then for the strong acid and strong base, this one here will be the buffering region. Okay, the buffering region, it's just from the beginning until the pH starts to increase rapidly. So as you see it here, it is increasing rapidly. So this is the buffering region. Keep in mind what we talked about buffering region. Now, if we have more than one hydrogen to release, so let's suppose that we have H3PO4 titration of, then the pH curve will look something like this. Is it a weak one? So we'll start as a curve up, and then we'll have a buffering region here, and then we'll move up. The first equivalence point is here, going to the second buffering region here, and then moving up to the second equivalent point because it is releasing hydrogen. Imagine that it is releasing the hydrogens one after the other, and then two, so equivalent point one, equivalent point two, and then we have the third buffering region here, and it is increasing, and it goes to the third equivalent point. So when you see something like this or something like this, that it's dropped, then you will count the steps, how many steps it go, or how many times does it go up, like in the case of the acid titration, or down in the case of a basic titration. And then you will pick that is, in other words, known as the polyprotic acid. So when you have a question that is asking you which one of those entities belongs to the titration, you will see if it is an acid, then will go up. If it's a base, will go down. And then you will count how many times will go up. This is the number of hydrogens that you have. And if it is a base, how many times will go down, and this is what it is releasing or accepting, able to accept as a proton. Make sense? Okay, so this is in terms of kind of a summary of the interpreting the pH curve on the titration. Keep in mind that titration is a reaction that is happening while buffer is solution that is resisting the change of the pH. So let's suppose that we have a case when we are dealing with a strong acid and a strong base. And this is what we have. So we have 100 milliliters of 0.125 moles per liter of sodium hydroxide. And then we have 150 milliliters of 0.100 moles per liter of hydrochloric acid. They are all in aqueous solution, and if I do not write it, then you assume that. Okay, you have seen this situation, strong acid, strong base, even in chemistry 20. So what I will do is I will combine whatever you have seen in the previous courses of chemistry with what we have said now in terms of the pH and all that stuff. Okay, so the first one will be to write reaction, okay, to write the reaction. So this reaction, keep in mind, since it is a strong acid and a strong base, is a completion reaction, is not an equilibrium, meaning that will go in one direction. So what do you have here is hydrochloric acid plus sodium hydroxide will give you water and sodium chloride, okay? And then as a second step, we'll find the number of moles based on the concentration. So the number of moles will be whatever is the concentration times the volume, okay? Or you can use stoic. I do not mind at all. So when we are dealing with hydrochloric acid, what is the number of moles? If you multiply 0.100 moles per liter by the volume, that is 0.150 liters, then liters and liters are cancelled out, and then we will have 0.015 moles of hydrochloric acid reacting with I will change the color so that you can see it with the number of moles of the hydroxide, sodium hydroxide. So then to find the number of moles of hydroxide, we'll go 0.125 moles per liter times 0.100 liters. So liters and liters is cancelled out, and then we will have 0.0125 moles of sodium hydroxide. Okay. Then when we are here, we work with the third step. Okay. The third step is defining which one is the limiting region. So which one will finish first? And since it is a 1-to-1 ratio, the one with the less number of moles will be completely gone, okay, completely used. So if this is the initial state, then defining or determining which one is the limiting reactant will give us the change that is undergoing. So the change, the smaller number of moles is for sodium hydroxide, correct? So then the change will be whatever is the number of moles for sodium hydroxide. 5 moles minus 0.0125 moles. Which means that what do you have on the other side of the reaction, on the product side of the reaction, you will have, even though that water doesn't affect anything, but keep in mind that they may ask you questions as how many moles are formed or what is the number of moles that is formed. So keep in mind this. And we will have a positive change of 0.0125 moles of sodium chloride, the salt. Are we good up to this point? We are faking or using the tricks and skills that we have on the ice table, but working with moles here. Therefore, at the equilibrium, what we will have is whatever was the initial mass plus the change, that in this case is negative. So we will have 0.015 minus 0.0125, and we'll have a number of moles at the equilibrium of 0.0025 for hydrochloric acid moles. For sodium hydroxide, since it was the limiting region, then we'll have a 0. And then, yes, we will have, even though that on this case, it doesn't really matter what it is, we will have 0.0125 moles of water, and we will have 0.0125 moles of sodium chloride. Both of them, of the product do not affect the pH. Why don't they affect the pH? This is HCl, this is NaOH, this is water, and this is NaCl. So both of them, the water and HCl, NaCl, sodium chloride, do not affect the pH. Why? Because they don't have hydrogen or hydroxide. The only one that affects the pH is this thing here, this product here, this that is left at the equilibrium. What is this? Is an acid or is a base? It's an acid. Is it a strong acid or so? It's an acid. It's a strong acid or is a strong base? It's a strong acid. How do we calculate the pH of a strong acid? We just go negative log. Remember the box that I told you? Negative log of the concentration of hydronium plus. What is the concentration? Remember, we have the number of moles here. What is the concentration? So will be negative log. Concentration is number of moles over the volume. So will be 0.0025 moles. And since we have, again, 1-to-1 ratio, because this is ionized into H plus and Cl minus, then we'll have the same number of moles that we have for HCl, we'll have for H plus over, what is the volume here? Let's go to the back, to the initial. What is the volume here of the entity, of the everything that we are having here? Is 100 plus 150. So 0.100 plus 0.150 will be the concentration of the hydronium. So the pH after you do this concentration, I have 2. You check with yourself and then you will have to. We will record it as 2.00 because I believe that we started with 3 sigdics, 333. So, and then for the pH, the sigdics are counted only the sigdics that are after the decimal point. Does this make sense? Strong acid, strong base. What we will see now is a weak acid and a strong base. Okay. Weak acid and a strong base titration. First of all, what we will do is we'll have, let's start with this. We have 100 milliliters of 0.1, let's add 2 more zeros here, moles per liter of HF with a Ka value of 6.8 times 10 to the power of -4. And then we are calculating what is the pH? What is the pH after you are adding 25 milliliters of 0.1 moles per liter of sodium hydroxide, a strong base. Okay, and then we'll go with 50, and then we'll go with 100, and then we'll go with 150, and then we'll call it a day. Okay, so let's start as a first step, write the reaction. This is a completion reaction because we have a strong base, not equilibrium. So HF plus, they are all in aqua solution, but for simplicity, if I am not writing, then you'll assume that. Then we will have, as a product, we'll have water and NaF in aqua solution, which is broken down into Na plus and F minus. Okay, as the second one will be number of moles. Okay, so as the number of moles, we will go with whatever is the concentration and the volume of each of them. So the number of moles for HF will be 0.01 mole and 0.0025 moles. And here we have 0 and 0 initial. Are you following? Good. And then the third step or the third set of action will be define which one is limiting regions. Since it is 1-to-1, the one with the smallest one will be the limiting region. So this means that in terms of the change, whatever is the number of moles for the limiting region will be used up. So the change will be whatever is the number of moles for sodium hydroxide. Since we are on the same side for HF, that will be negative, the same sign, and 1-to-1 ratio will be the same number. And then we have, moving to the product, we will have a positive 0.0025 moles of water, even though that it doesn't affect the pH. For the sake of being fair, we write that down. And for NF is the same. Okay? That means that at the equilibrium, what we have is, at the equilibrium, what do we have for HF? We have 0.01 minus 0.0025, which is 0.0075 moles. This is all used up, so we don't have anything here. Water, it is still 0.025, even though that we don't use that at all. And then what do we have for NaF is 0.025 moles. So now, this is what we have for the weak acid. This is what we have for the strong base. This is what we have for water that doesn't affect the pH at all. And this is what we have for an AF in aqueous solution, which is never as NaF, but it is always as Na plus and F minus. Okay, so see now what do we have here? We have a weak acid and its conjugated base. What is that case? What is it? Is a strong acid, strong base, weak acid, weak base, or is a buffer? One of the five will be. When we have the weak acid and its conjugated base, what do we have? What do we have? What did we say that we have when we have its acid and the acid and its conjugated base? Yes, it is buffer, because always a buffer is formed with weak acid and its conjugated base. As soon as you see some concentrations of weak acid and its conjugated base, then boom, it's a buffer. Okay, so if it is a buffer, since it is a buffer, then what we will do is we will calculate the pH using Henderson and Hasselbalch. So pH is equal to pKa plus log concentration of A over concentration of the acid. But since we are dealing with the ratio, we can even write it as pKa is equal plus log of number of moles for conjugated base and the number of moles for the acid. So now that we know everything, pH will be pKa is negative log of Ka plus log of Na minus number of moles over number of moles for the acid. Keep in mind, as I said, we can do that. We didn't do this in the previous example because we didn't have the ratio. We need the concentration. And the concentration on the previous example is always moles per liter. But since we have the ratio at the buffer as Henderson and Hasselbalch's formula, we are free to use the number of moles. Okay? So this will be negative log of whatever is the Ka value, which was 6.8 times 10 to the power of negative 4, plus log of the conjugated base is 0.0025 moles of the conjugated base F minus over 0.0075. So instead of now doing again the ice table, you'll boom have the pH of the buffer because this is a buffer with using the Henderson and Hasselbalch's formula. So pH will be 2.7. And then you can say that, is this still a buffer or not? Is this a buffer solution even on this stage? Yes or not, by comparing the TKA with this value to be between plus minus 1 of the pKa. Okay, so now let's see a case when we are at the midpoint of the, so we are adding half, okay? And this midpoint of the equivalence point. It is kind of important that when we are looking at the graph here, if the equivalent point is somewhere in here, this volume, then the midpoint here, the half volume of equivalent point to be calculated. And this is what we will do now. So we'll continue with this question when we had the weak acid and the strong base titration. And then we will see what is the pH. So the given is 100 milliliters of 0.1 molarity of HF. And then what we are doing is we are adding 50 milliliters of the same molarity of the strong base. Now, a shortcut on this, when you are at midpoint, when you have the same concentration and you are at midpoint in terms of the volume, is that the pH is equal to pKa. So will be negative log of Ka, which will be 3.70. Okay. However, this is a question that can be done in 5 seconds if you know this. Now let's justify this, why it is like this. Let's take a look at the let's say the ice table of moles. So HF plus NaOH going to completion to form water and NaCl. Oh, NaF, not NaCl. Oops. NaF. Okay. So in terms of the number of moles, we have 0.01 mole of HF. We have 0.005 moles of, because we are in 50 milliliters here. And then we have 0 and 0 initially. The limiting reagent is the strong base. So the change will be whatever is the number of moles for the strong base. For both on the reactant side is a negative 0.05 moles, while for the product side is a positive 0.05 moles and 0.005 moles positive. And now at the equilibrium, what you will have is 0 for the strong base, because it is all used up, and 0.005 moles for the weak acid. Yes, so we will have 0.05 moles of water, which doesn't affect the pH, and we will have 0.05 moles of NaF, which is the in aqua solution is actually Na plus and F minus. So you see here that at the equilibrium, you have 0.05 weak acid and 0.05 its conjugated base. Since it is the case that we have the weak acid and its conjugated base, boom, this is a buffer. Since it is a buffer, we use Henderson and Hasselbalch formula. So pH will be pKa plus log of the concentration of conjugated base over the concentration of weak acid. Since we are dealing with a ratio, then we will have pKa plus log of the number of moles for the conjugated base over the number of moles for the weak acid. But notice what we have here. We have the same number of moles, okay? So this will be pKa plus log of 1, because you are dividing two things that are the same, okay? Log of 1, if you are entering it in your calculator, you will have equal to 0. So at the half point, when you have the same concentration at the half point of the equivalence point, you will have pH is equal to pKa. Now, if they are not with the same concentration, then you have to go through the steps. But if they are with the same concentration, you can see and calculate and then prove and choose to use 5 seconds into it, saying that pH is equal to pKa, or 5 minutes, whatever you want. Those questions that we are looking at now are the hardest one that you will see in terms of the, I will say, acids and bases calculations. But titration is the one. So now, what we will see is what is at equivalent point. So we have 100 mils of 0.100 molarity of HF. And then we have 100 mils of 0.100 molarity of NaOH. This means that we are at the equivalent point, at the point where the inflection is happening, at the point where the number of moles of both acid and the base are the same. And you can see it's the same volume, the same concentration, and then you have the weak acid and the strong base. Like in everything, we will start with the reaction. It's a completion reaction because not an equilibrium, because you will see that everything will go into the product side. So H2O plus HF. Okay. In number of moles for each of them, 0.01 mole for hydrofluoric acid. No, yeah, hydrofluoric acid. 0.01 mole for sodium hydroxide. And then initially we have 0 and 0. Then, which one is limiting region here? They are the same. They are equally the same. When they are reacting, you see here, you can pick any as the limiting region because they are the same number of moles, and it is a 1-to-1 ratio, so 0.01 mole will be used. And then when we move to the other side of the reaction, we will form 0.01 mole of water along with a 0.01 mole of what is this? This is not HF, this is sodium fluoride. Okay. Now at the equilibrium, what do we have is 0, because 0.01 minus 0.01 is 0. 0 for both the weak acid and the strong base. And for water, we will have 0.01 mole. And for sodium fluoride, we'll have 0.01 mole. We are at the equilibrium, okay? So 0 moles for HF, 0 moles for NOH, 0.01 mole for water, which doesn't affect at all the pH value, and 0.01 mole for sodium fluoride. That is in aqueous solution, meaning that it is broken down into sodium and fluoride. Great. What do we have here? Do we have, listen to what I'm asking, strong base, strong acid, weak base, weak acid, or buffer? What do we have here? One of those 5 will be the one that we will deal with. And what do we see here? We have a strong base. Sorry, weak base. A weak base, not a strong base. Since we have the weak base, I show it to you what is the way, the shortcut that we calculate the concentration of hydroxide as the square root of Kb times the concentration of B minus. Okay, now, do we know Kb? No, we don't. We do not know Kb, but we can find out what Kb is using the auto-ionization of water. That Ka times Kb is equal to 1.0 times 10 to the power of negative 14. Knowing Ka as 6.8 times 10 to the power of negative 4, we can find Kb as 1.0 times 10 to the power of negative 14 over 6.8 times 10 to the power of negative 4. When you enter this in your calculator, you will find that Kb is 1.47 times 10 to the power of negative 11. I keep more than one digit after the decimal point just for the sake of being safe, not rounding too fast. So this will be the first thing in this question or in this formula. The second one will be the concentration of the base. So the concentration is moles per liter. We do know what is the number of moles because we found it through our moles ice table that we have 0.01 moles of F minus. So 0.01 moles of F minus over the liters. So now what we are doing is we are adding 100 milliliters of HF and 100 milliliters of NaOH. So will be 0.100 for the HF and 0.100 for NaOH. Okay, so then you will find the concentration as 0.05 moles of F minus over liters. Now that you have the two pieces of the concentration of hydroxide, we can find the concentration of the hydroxide as the square root of 1.467 times 10 to the power of negative 11 times 0.05 moles per liter. The whole thing is squaring up, and then I have here as the concentration 8.6 times 10 to the power of negative 7 moles of OH minus per liter. Now that we know the concentration of OH, we can calculate the POH as negative log of the concentration of OH, or negative log of the answer, 8.6 times 10 to the power of negative 7. And this will be, based on my calculations, 6.1. Now, if we are looking for pH, then we'll use the fact that it is 14 minus pH equal to 14 minus 6.1 equal to 7.9. Wait a minute. Was this something that you were expecting? Because you are dealing with a weak acid and a strong base. Were you expecting that the pH will be greater than 7? Yes or no? Since the power goes to the strong base, so weak acid, strong base, then the pH will be greater than 7. And it is greater than 7. Every number, every calculation that you are doing, you have to think and see what is this number? Is this according to my logic, yes or no? Does this make sense? Bell goes, please stay. So the summary, if you are ending with a strong acid, then you calculate pH as negative log of the concentration of proton or negative log of the concentration of hydronium. They are in aqueous solution, so if you are dealing with a strong base, then you calculate POH as negative log of OH minus, and then from here, using the fact that pH is 14 minus POH, you can calculate pH. Okay, if it is a weak acid, then the pH is calculated as, or the concentration, not just the pH, the concentration of the concentration of proton or the concentration of hydronium will be using the shortcut. So the square root of Ka times the concentration of proton. If we are dealing with a weak base, then what we will do is, again, we will use the shortcut, the formulas that I showed you yesterday, and we worked yesterday, plenty of examples. So weak base will be the concentration of hydronium, oh sorry, not hydronium, but hydroxide will be the square root of Kb times the concentration of the base. And this is not the concentration of hydronium, but this is the concentration of the acid. And if it is buffer, where you have the weak acid and its conjugated base, you see, you write the reaction and you end up with the weak acid and the conjugated base, then you will use Henderson and Hasselbalch formula as pH is equal to pKa plus log of the concentration of the conjugated base over the concentration of the acid. This is the question that we just did before, is the hardest one. Practice on it, do it several times, and you will be great on the calculations of titration for acids and bases.